Hi, I'm Pienaar from the University of Vienna, Austria, and this is work in collaboration with Tim Relf from the University of Queensland, Australia. I'm going to be talking about an experimental proposal to test a really unusual theory of gravitational decoherence. Is time travel possible according to the laws of physics? In Einstein's theory of general relativity, it might be possible for time to form a closed loop, a closed time-like curve. But to completely answer this question, we would also need to know what happens to quantum systems that go back in time. In 1991, David Deutsch developed a model of just such an occurrence, in which a single quantum bit, or qubit, goes back in time and interacts with itself. Astonishingly, this does not lead to any logical paradoxes, even if the quantum bit tried to prevent itself in some way from time traveling, there would still be a consistent solution. This comes from the magic of quantum mechanics. However, there is one or two strange consequences of this model. One of them is that it's nonlinear, and the superposition principle no longer holds. And the other is that it's non-unitary, which means, just like in a black hole, information can be lost. That's really neat, but how could we possibly test such a theory? For one thing, it only describes non-relativistic particles, and for another, where would we get our hands on a time machine? Fortunately, both of these obstacles can be overcome. First, we need to generalize Deutsch's model to relativistic fields. The most relativistic field is quantum optics, which describes photons, or particles of light, and these always travel at the speed of light. We can generalize Deutsch's model to quantum optics by taking the usual quantum optics field operator and giving it an extra degree of freedom that makes it commute with itself after a certain amount of time has passed. This gives us a nonlinear modification of quantum optics, and we can see how it behaves in gravitational fields. It turns out that we don't need time to bend all the way back on itself to begin seeing the strange effects of Deutsch's model. In fact, it's enough to look at the time dilation caused by Earth's gravitational field, and we'll already see some decoherence predicted by the model. All we have to do is look at entangled light in Earth's gravitational field, and we can potentially test Deutsch's model. We propose an experiment in which entangled pairs of photons are produced on the ground. One of them is detected on the ground, but the other is sent into space to a satellite where it is detected. The signature of entanglement between the photons is found in the count rates of the pairs of photons, because every time we detect one photon on the ground, we expect to detect another one in space. So by looking at the count rates for the pairs of photons, we can tell whether decoherence is occurring, because we would see the count rates drop. If we see this drop in count rates, then we know that there is a deviation from the standard theory. And this would provide a signature of a model like Deutsch's model. Thanks for listening, and if you want to know more about the proposed experiment, please check out the paper. Or if you want a less technical description, you can also check out my blog.